Thanks for your patience and good afternoon. So we are good to start. Today is our first Tutte Colloquium of the spring term, and this is distinguished Tutte Colloquium. And we have honor to have Professor Katya Scheinberg to give it. So Professor Katya Scheinberg works at School of Operational Research and Industrial Engineering at Cornell University, and soon she will be joining Georgia Tech. Before that, Professor Scheinberg worked at Lehigh University and IBM TJ Watson Research Center and obtained the PhD degree from Columbia University. Main interest of Professor Scheinberg is developing theoretical analysis for practical algorithm and continuous optimization. She is Informs Fellow, a recipient of Lagrange Prize, the Farkas Prize, and the Outstanding Simulation Publication Award. She services as Editor-in-Chief for Mathematics of Operational Research and Co-Editor of Mathematical Programming and Chair of SIAC OPT. So please welcome Professor Scheinberg.
Right, so the first time I was giving it was to a whole bunch of statisticians and computer scientists and electrical engineers. And I think it's like almost no overlap here, right? It's like mathematicians and optimizers. Okay, great. So very different perspective, but still the same talk. We'll see what you think. And the talk is actually also very kind of high level because we are trying to put together a survey on these stochastic oracles. And so as I'm thinking through it, I'm trying to see how we should view them and why and like what it's all about. So this is basically, I'll try to tell you a story and then I will be very happy to question the story, ask, all sorts of questions and whatever. So, okay, so let's start with just standard optimization. And what is an oracle in optimization? So there's this word oracle, which everybody actually understands somewhat differently. So I want to project a certain understanding that I would like you to think about. So we have a optimization problem where we're trying, it's unconstrained optimization, we're trying to optimize function phi. And let's say you have the function and I'm writing a code that will optimize this function for you. And we have to have a handshake about how we communicate this function, right? So these are what oracles are. So I say, well, from time to time, I will ask you to compute function value for me. And that will be the 0th order oracle. And then from time to time, I'll ask you to compute the gradient of this function for me. And that will be the 1st order oracle. And you promise to do that. And then that's okay, that's all I need from you. And then I will go ahead and, write my code. More often than not, you'll say, sure, I can do this, but I cannot do this accurately. I'll have some error because whatever computes my function is really a complicated fluid dynamics code or whatever with discretization. So there's usually an error, and for decades, optimizers, especially on practical real engineering applications, have been trying to work out what can we say about this error and what does it mean for optimization algorithms? So these are inexact oracles, and very often we simply assume that there is some kind of a bound, deterministic bound on this inexactness. So it comes from round-off error, discretization, and maybe you have control over this bound. More often than not, people kind of assume that you can control it somehow. So there's a lot of work in trying to figure out how much error you should tolerate if your algorithm wants to achieve some kind of accuracy, right? Okay. So this is all being nice and good. And why, well, okay, so what do we do with deterministic information like this? And I'm talking about 1st order algorithms, but much of what I'll say will carry over in some sense to 2nd order, but I will not talk about this at all because things get, just more messy. So what do we do with information such as gradient? We have gradient descent, right? What does gradient descent do? Just takes steps downhill, right? So you sit somewhere on a slope and you start going downhill until you're somewhere in a flat area. I'm talking about convergence to essentially areas where the gradient is 0. That's all we can do. I'm not talking about global optimization. Okay, so this is the gradient descent algorithm. And as anybody who's tried it knows that you need to decide this on the step size. So gradient is something that you get from your oracle, and then you need to decide how far you're going to go. And essentially, you can, okay, let me skip that part. The key part comes from the fact that if my step size is small enough, and small enough being smaller than 1 over the Lipschitz constant of the gradient, as probably many of you know, since you've all learned gradient descent, I'm sure, you will guarantee a decrease in your function value, right? So your function value is guaranteed to decrease by this much. So this is the size of the gradient. If the gradient is big, then the norm squared is certain fixed amount, and this fixed amount is how much gain I get in my objective function. Okay, so it's important because then I have guarantees, right? Okay, so all that is good. Now, if I have that is something that is the estimate of the gradient, let's say, and not the gradient itself, I can still have a descent algorithm of some kind, as long as this direction is really direction of descent. And this is more or less, this is a very kind of simplified situation explaining what I want from my algorithm, from my gradient, from my direction. So basically, it needs to make a certain acute angle with the gradient, right? So I need to, I take a step, and again, I have a condition that if my alpha step is small enough, this time it's theta over L, then I will have again a gain of this amount. So it is all very well known. I just want you to focus here on the fact that my step size now has to be smaller because this is a constant that may be relatively close to 0. I want to make sure that it's definitely not 0, otherwise I don't have descent direction. But that makes my step size smaller. That makes this reduction smaller. And what is more, kind of, well, it's not necessarily more important for this talk, but in general more important is I also don't even know what this theta might be, right? And I also may not know L. So somewhere, but there is a threshold, right? Alpha. Sorry, threshold for alpha after which the reduction happens. Okay, so this is all deterministic. What happens now in stochastic world? So now due to machine learning and all kinds of other applications, more often than not, we have some stochastic information about the function and not deterministic one. So what does it mean? It means that instead of computing the function value, I compute some sort of a value, right? My oracle. So I'm writing the code, you're writing the oracle for me. You're going to say, okay, I have the oracle that will estimate phi, but it will be stochastic. So it will have some kind of randomness in it. Same thing for the gradient. And then what do we say? Like, what do we agree on? Before, in deterministic case, you said, okay, I'll have an error that will be bounded by some value. Now what do we say? Well, this is the things that happened maybe even 10 years ago, whatever. The assumptions were very basic. The assumptions usually would be that the estimate that you give me is unbiased. So an expectation, it gives me the true value, and that it has a bounded variance. The same thing for the gradient. The estimator is unbiased, and the variance of the estimate is bounded by some value, right? Fixed value. These are very convenient to make, and first thing that's what you'll do is you make these assumptions, but these assumptions are pretty bad. Because first of all, they don't hold in many cases. And second, they're also not necessarily very informative because like, what should this value be? I mean, is it large, is it small? So I will really focus a lot in this talk about bounding this particular variance. And in fact, I would want to look at kind of more modern conditions on these oracles. So the function values can have a bias. They often do. In fact, I should not, well, it doesn't really matter, but I should put actually not the phi here. Sorry, I should put here instead of phi, I should put the expectation. So this is the bias, so the phi and expectations are not the same thing. And this is the variance. The variance on the function value does not have to be bounded, but often it is. That's not a problem. The gradient, on the other hand, the function, the gradient is also often biased. So this is definitely something I'll talk about today, because in many, many applications you have a bias here. And the variance term is going to be split into two pieces. So this is basically what is known as an absolute error, and this is what's known as a relative error, right? This is the error that is scales with the gradient. This is the error that does not. Okay, so this is, I'm arguing that it matters how we look at the oracles, okay? No questions, okay, so maybe it's all very simple. So, okay, so why does it matter that we look at it this way? So now we have this MC, MV, and the epsilon G. If I now look at what happens with the function value in one step of a gradient descent algorithm with this particular GK, so GK now is my random estimate. If I take a gradient descent step, or whatever, well, not gradient descent, but descent step with this thing, I will get this expression. And this expression, what does it, in expectation, right? So in expectation, my function value will decrease by this amount. What is this amount? This is negative, right? This is negative, as long as this term is not bigger than 1. So if this term is smaller than 1, then this is a negative term, and it's proportional to the gradient squared, which is exactly what we have in the deterministic case. Now, this is positive, and this is positive. So first thing we notice is that if this happens to be 0, so if my error in the gradient is only a relative error, there is no this term here, then I don't have this, and I just have kind of a nice descent, as long as my step size is small enough. So small enough, 1 over L, and then the bound, this MV constant, right? Okay. It will come up. So if I only have relative error on the gradient, even though it's stochastic, I can have deterministic behavior of my algorithm, except for my convergence rate. My step size is going to be just smaller. So my convergence rate is going to be smaller by basically proportional to this. Okay, that is obvious, but it's actually surprisingly how many papers have been written where this fact is reused different ways for this, different setting. But it really just boils down to this. So if you look at Oracle in the right way, you have this convergence property. Now, if you don't have, what happens, like the classical stochastic gradient, if you don't have MC equal to 0, then you cannot converge to an optimal solution without decreasing step size to 0. Why? Because what you're trying to do is basically you're trying to decrease, so you're going to have a telescopic sum adding up all the progress you're making in the algorithm. And you want this term to accumulate and this term not to dominate, basically. So you're making sure that the sum of alpha k's is divergent, but the sum of alpha k square is convergent. So you need alpha k to go to 0 fast enough. So then this term is not going to be, eventually it'll converge to something finite, and this term will eventually dominate and create progress. And then there's also this term. So this term is nothing if epsilon g is 0. But if epsilon g is not 0, then you cannot make this term finite, because there's alpha k here. There's no alpha k squared. But this term is not going to be dominating until your gradient becomes smaller than this epsilon g, right? Because this is gradient times epsilon g. This is gradient norm squared. So when gradient norm is bigger than epsilon g, then this is bigger than this, you're fine. But other than that, then you, at that point, all bets are off. And again, if you just look at the right constants, you will know exactly what will happen to your algorithm. if this epsilon g is your bias and there's nothing you can do about it, then you'll run your algorithm until you converge to somewhere where the gradient is smaller than epsilon g. Right? So it's a neighborhood of convergence. That's what, you know. So you can look at it this way. Like you can say, if I want to converge to a certain neighborhood, I have to make sure that my oracle bias is small enough. Or you can say, if you're shaking hands about the oracle that you write, you say, I cannot provide you anything with this bias smaller than 10 to minus 3. And I say, OK, well, you know, you're going to get what you get, right? And this is roughly what you'll get. OK, any questions about this? OK, so this is stochastic oracles. Now we're going to talk about where to find them, right? So the machine learning setting. There is quite a lot. So what is machine learning? You essentially optimizing an expected loss function where loss is measured by your classifier on some data point. Data comes from a data set. You select a mini batch of B, and then you evaluate basically, you know, average approximation, stochastic average approximation of your function, the gradient, based on that mini batch, right? And this is what gives you the estimate of the gradient. This is what gives you estimate of the function. So it is become fairly common, and it's really true for many applications, for most applications that this bound holds. But there is a whole host of papers that assume for machine learning specifically that MC is 0. Where does this idea come from? So it comes from that in overparameterized neural networks, basically when you reach a point X for which the gradient is 0, then it's also 0 for every realization of the gradient for every data point. It's very weird. It's a strong assumption. Nobody has ever actually proved it for any large neural network because we don't know anything about them. But there are empirical statements that this is true. So somehow we believe that often enough in machine learning applications and large-scale ones especially, this term somehow is small. And if we assume that this term is small, as I told you, we can derive all kinds of deterministic behavior bounds on the stochastic gradient method. So stochastic gradient method converges slower than the deterministic one, generally. But if MC is 0, then the rates of convergence are the same. What is slower is basically the constant. So in deterministic case, we don't have this MV thing, it's 0. And in a stochastic case, we have this MV here. So how do we control this MV? By increasing the size of the batch, right? The larger the batch, the smaller MV, clearly. So this is where you can very simply see that there's no free lunch. In a sense that the more I sample in every iteration, the longer the step sizes, and the proportions are exactly the same. So I can sample 10 times more per iteration. My step size is going to be 10 times larger, theoretically, right? That's it. Or if I sample less, that will be 10 times smaller. So I will not win. Now, we do win to a certain degree, but the reason like you pick a batch size of, say, 128 is because of cache, right? This has nothing to do with computational complexity. It's really the implementation complexity that comes in. But from theoretical point of view, at least, it's very clear. If you treat the oracle in the right way, it's very clear that you will not win one way or another. OK. Different setting with the same thing. So this setting will not appear useful until I'll switch gears a little bit to derivative-free optimization. But so let's say you want to now estimate the gradient in a subspace. There are various ways to do this. So you have, you're in a very large dimensional space. You have a, I don't know, 1 million dimension. And you somehow want to work in a 10-dimensional subspace. So how do I generate this 10-dimensional subspace at random? I can pick 10 random coordinates. That would be this thing, right? So my little n is 1,000,000 and my big N is 10, just to confuse you. So big N is small, little n is large. So I pick random coordinates. I can pick Gaussian, 10 Gaussian directions. I can pick, or Gaussian vectors. I can pick 10 directions on a unit sphere. Directions would be kind of the same, but the length of the vector will be different, so that would change things. Or I can pick 10 orthogonal directions with a random orthogonal rotation, right? So these are the 4 things that I will look at. And then what I can do is I can just compute the projection of the gradient on each vector and sum them up. What do I get? It's going to get, I mean, it's just a way to compute something in a subspace. You'll see in a second what it is. So there is randomness here. This is a random estimate of the gradient. In all cases, it's a stochastic gradient. So in expectation, it's actually going to give us correct gradient. So you can show that. That's pretty easy. That in expectation, all of this, all it gives us a correct gradient. In terms of variance, here are the bounds. So these two and these two are kind of relatives. So these two are almost the same, n+1 and -1, whatever. But what do you see here? So there's no absolute error. It's only relative error. So when the gradient is 0, then there's no error. That's great. And this error basically, so this is 1,000,000. This is 10. OK, this is a large error. As n goes, as big N goes to infinity, this error will decrease, but it will never be 0. This is different. It is basically going to become 0 as soon as big N becomes little n. Why is this? Well, because basically if the directions are orthogonal, then what I have here is really a projection of the gradient onto the random subspace. If the directions are not orthogonal, then it's not a projection. It is something else. So that not projection is slowly approaching the true gradient as the number of directions increases, but it's never exactly the gradient. Whereas this one, because these directions are orthogonal, it's just a projection. So you will, as soon as your space, random subspace of the same dimension as the space is the space, right? So I'll just compute the gradient. That's it. OK, so what is of interest here? Well, not much in this case. So the one thing that is of interest is this bound, because basically this is computing coordinate gradient, right? So projection on a random coordinate subspace is basically just computing a few elements of the gradients. Sometimes it's cheap to do that for your problem. You can compute the few elements of the gradient instead of the whole thing, and then you do a block coordinate descent. So you do block coordinate descent. So let's see what happens. Let's say you compute 1 coordinate of the gradient. So computing n coordinate of the gradient is n times more expensive than computing 1. It's not always the case, but let's say it's the case. So computing 1 coordinate is cheap. I compute 1 coordinate, and then I apply this method. This is my MV. My step size is going to be 1 over MV smaller, right? So this is 1, this is 1. So this is basically order of little n. So this is order of 1,000,000, if I have 1,000,000-dimensional space. So if I am now computing 1 coordinate at a time, my step sizes are going to be 1 over 1,000,000 compared to the step sizes of the full gradient. It is, again, nothing new. Nesterov has done analysis of randomized block coordinate descent in 2010, exactly has this result. But this result just comes out from looking at the oracle in this way. OK? OK. So where does it get more interesting? these four, why did I look at these four different random subspaces? It gets more interesting in derivative-free optimization. So what happens in derivative-free optimization is that you don't get gradient estimates at all. So I'm asking you for oracles, and the only oracle you can provide is a function value, and not exactly, right? But you cannot provide anything useful about the gradient. So then I have to work on providing my own gradient estimation myself, because it's an optimization algorithm. It's kind of hard to do things without any gradient information. And the thing that I'm sure everybody here had seen before is forward finite differences, right? So you just compute gradient estimation by finite differences. So if I'm picking a direction and I want to compute a gradient estimation along this direction, so projection essentially of the gradient on that direction, I just need two function values, the one at x and the one at x plus a little bit along that direction. So I take the difference, I divide by the step size, I multiply it by the direction, and this is the estimate of my directional derivative, so my projection of the gradient onto the space U. Okay. So this is the gradient projection onto U. This is what I've computed. There's a difference between the two, because obviously, right? I mean, this is finite differences. Actually, this is not what I have computed. This is what I've computed. This is what I would have computed if I didn't have an error. I also have an error, so I have two terms here. This term is bias. I cannot do anything about it. This is not biased. This is random noise, because I assume that these things are random and actually unbiased. Well, I don't have to assume that it's unbiased, but if I assume that they're unbiased, this will be unbiased noise. If I assume it's biased, there'll be a bias here as well, right? So I can make, okay, sorry. You do very small, things with Taylor series, and you get this bound. This bound says that basically my bias is bounded by Lipschitz constant of the gradient times that step size. And my noise is bounded by the variance of the noise, assuming that's basically what my noise is, stochastic noise is bounded with, divided by delta, right? So now I have, the bound on essentially this error, which has a trade-off, delta. I want delta to be small, but if I make it very small, then this term will explode. So you can say that, okay, well, I know what delta I should pick. It should be square root of the sigma, right? Yeah.
Can I just ask, why do you have a xi naught plus and a xi naught? Why not just one xi naught?
Because I don't assume that this is the same realization. That's a very good point. So, yeah, right. So that's a whole other thing. If you actually can compute the function value with the same random number, whatever, common random number is called, right? So in simulation, they use it very often. It's not going to buy me necessarily all that much in what I'm talking about, but it's a special case, right? That I can actually compute it with the same realization. Yeah. I mean, think about it, yeah, if I'm simulating something, some behavior, maybe I can fix my random number sequence and simulate it and get both. But if I don't know, if the situation changes somehow in my simulator, then I cannot do it. Okay. All right, so this is central finite differences. It's basically a similar thing. It's just that it's more accurate. It has better behavior, so people tend to use it more, especially in simulation optimization. It's quite common, and you can derive all the same things for it. The difference is that you compute the function value like going in two directions, away from x, and then this piece here is bounded by the Hessian, the Lipschitz constant of the Hessian, not the gradient, and delta squared. So the balance between the optimal delta is no longer the square root of sigma, but the cubic root of sigma squared. But it's fine. Okay. Now, I'm going to put this all together. So the interesting part is that all these things have been done in the literature in different papers. And again, since we're trying to put them together in kind of a survey, I think it's a very nice way to look at them this way. So I have 4 different ways of generating random directions. And then I have a way to compute approximate gradient by using finite difference approximation along these directions. So this, for example, Gaussian smoothing became super popular after a paper by Nesterov and Spokojny in 2017 officially. I think it actually existed before. Everybody's using it left and right. It's like that has become the only way of using zeroth order optimization. Is just like you compute Gaussian directions, you compute this finite difference approximation, and that gives you a stochastic gradient, and boom, you can prove things about it. Unisphere is just a little bit better behavior, but it's a similar idea. Then you can also do the same thing along coordinates, which actually people have done in simulation optimization quite a bit. You can have these coordinates not be, you can just pick the whole space. You don't have to pick the subspace. It will be what's known as Kiefer-Wolfowitz back in the day. So there are a lot of different things. This Haar matrix is basically random rotation, as I said, or for orthogonal ones. And then you just go ahead and plug everything in. So then you automatically get, so this is your bias, this is your noise that is absolute noise, and this is the noise that is relative noise, right? So this is my MC, this is my MV, this is my bias. And I can plug it in and see what happens. And so what happens essentially is, yeah, well, you know, you can, yeah, that's basically what, well, this is actually square root of MC. This is square root of MV because I don't have a square here, so roughly this is what it is. But if I don't have this piece and this piece, I need to pick alpha k less than 1 over L MV, right? So I will have just slower behavior. If I have, if I don't have this piece, I will have a bias, but I can make this delta go to 0, and then I can converge to an optimal solution. So basically, if I don't have a noise in the objective function, I can have a essentially deterministic type behavior. But then if I do have a noise in the objective function, then I will have the exploding MC, right? And if MC is exploding, I can no longer just do what I did with the stochastic gradient. I have to do other tricks, but again, I can do something a bit smarter because MC is exploding at the rate of 1 over delta. Before, I was trying to make sure that alpha k squared converged to, was summable. Now I can make sure that this thing is summable. And again, this is something that has been done in simulation optimization kind of piecemeal, but you can put it together and see basically how you can have a nice convergent scheme, basically. Questions? Okay, so how are we doing with time? Okay. Right. So things now that we can apply the same things to, the same ideas to, that are less standard. Polynomial interpolation. We've done this, a lot of that in derivative-free optimization because various reasons, but what is polynomial interpolation? It's basically kind of generalization of your finite difference approximation. So you take, let's start with exactly n points, n plus 1 points in a n-dimensional space. And you can fit a linear model into this. So you fit linear polynomial. And to do that, you solve a system of linear equations. And essentially, you do that. And you have these function values where, so you have n plus 1 points where you evaluate your function with some error. You compute the gradient estimation based on solving system of linear equations, blah, blah. You get this bound. This bound is exactly the same as the bound for you would get for finite difference approximation in a full space, not in a subspace, except for this inverse of this matrix, the norm of the matrix U. What is U? U is the matrix of, basically it's like you pick one point, you pick as x0, and the rest, so you have n plus 1 points, right? One of them is the center, and the other ones are directions. So U's are basically these directions, and you make a matrix out of them. So when you have finite difference, or Haar, that U is orthogonal. So that thing is 1. And so you have, you basically recover exactly the same situation as finite differences, except for if you don't pick your points very well, then this error is larger. Why would you ever do that? Why would you ever do such a strange thing as pick points that are not orthogonal? Because it's worse. Because this allows me not to, so like imagine I have an optimization algorithm, I have n plus 1 points where I know my function value. Now I compute a step, I compute another point, I compute one more point. Instead of abandoning all n plus 1 points and computing new n points, because my finite difference approximation requires me to compute orthogonal set of function at orthogonal set of points every time. So I move, I have to compute n points again, compute n function values again, n calls to the oracle, it's expensive. Instead of that, I can maybe just adapt my sample set. So I have a sample set of n plus 1 points, I compute one more, I throw one out, I have n plus 1 points again, I move more, I throw one out, I have n plus 1 points again. Is that clear? Or am I losing everybody? And then I cannot guarantee that these directions are going to be orthogonal. But on the other hand, as long as this U matrix does not have exploding norm, I still have bounds on my first order approximation. I can do the same thing if I have random subspaces. I'm not going to go through that in great detail, but basically the whole idea is that you can now have the same linear interpolation in a random subspace, and your errors are going to be roughly of the same order as long as the matrices that you're dealing with or directions that you're dealing with are not too collinear, basically. Okay, so now why am I telling all these things? Again, there are plenty of algorithms that use linear interpolation, and of course some of them are doing something more elaborate and it may be not so easy to analyze, but if I just plug in stochastic function estimates and this sort of analysis and random subspaces, at least I can easily expect what kind of behavior a gradient descent will have based on these oracles. Okay, so if again, this is all about you have these oracles, they come from different places, but if they are characterized in a certain way, I should know how to analyze a gradient descent based on these oracles. Okay? Now, just in the last few minutes, a little bit more, sort of cool things. So not all oracles, at least immediately, have the same guarantees as I showed you. And yet we still can do analysis with them, and this is kind of the analysis I've been focusing on the previous 10 years. And it was motivated actually not by linear interpolation, by quadratic one, but I'll just show you the linear interpolation idea. So if I have, it's a very, contrived example to some degree, but so let's say I'm trying to build a approximation of a gradient using linear interpolation, solve system of linear equations. If I need to construct this gradient more or less accurately in n-dimensional space, I need n samples, right? N plus 1 samples. So million dimension, million samples, maybe a lot. Now let's imagine that my gradient actually is not expected to be dense. It's expected to be nearly sparse. I don't know the sparsity pattern, but somehow it's nearly sparse. Then we know from compressed sensing and all these wonderful things that if we sample points somewhat randomly, or if we generate the system of linear equations that has nice properties, and then we solve this problem, so we minimize the L1 norm of the gradient subject to this underdetermined system of equations, we can recover sparse gradient in much less than n samples. So it's actually log n samples, or s times log n sample, where s is the sparsity. Okay? So any questions about the settings? The standard kind of sparse signal recovery kind of situation. I have a sparse gradient in a million-dimensional space. If the number of non-zeros in the gradient is 100, I don't need to sample nearly as much. And what do I get? So let's say I sample only 1,000 points instead of 1,000,000. What do I get? I get some kind of an estimate, which is random because I had to sample randomly, right? And it has all the properties of the right kind of subspace gradient, because like basically with high probability I've recovered it correctly, but with high probability. I don't know, I mean, again, people who specialize in this kind of analysis maybe know a good way to bound the variance, but I don't know it. I know that lots of results are just with high probability. So now we're in a little bit different situation. We have this very nice bound, but it only holds with high probability. I don't know what happens otherwise. There is another example of the same kind, kind of the same kind. Now I am computing, it's a robust gradient estimation. So I'm in machine learning setting, I have distributed data on 4 machines. I'm computing my gradients on individual samples or batches coming from these 4 machines. One of these machines has been corrupted. It used to be called Byzantine machine, but apparently it's not right anymore. It's offensive somehow. So it's been corrupted, and it sells me maybe garbage instead of correct gradients. If I start summing gradients up, I'm going to get wrong information. So instead, I can do something like geometric median computation of the gradient, which has nice properties. And basically, the whole point is that, again, I will recover something of the first order. I mean, that is the first order information, which is sufficiently accurate here. Now I can bound the accuracy. I'm being very vague here because I have to define a whole bunch of things to specify what this error would be. But basically, that error holds with some probability. And I don't necessarily know how to otherwise bound it. And a lot of papers have analyzed this kind of gradient descent with these gradients as well. Well, not a lot, but significant number. And again, we can, you know, take out the gradient and look at it basically from this perspective. So I will, I don't know if you have the patience to absorb this, but so now I want to think of maybe a broader way to defining these oracles, and this is not necessarily the final way of doing it, but essentially we're back to the situation where I am writing code, you're writing the oracle, we're shaking hands about something, and now we're going to shake hands about the property of the oracle in a slightly more high level or abstract way. I'm going to say that I will give you a pair of numbers, for example, or maybe I'll give you a distribution. I don't know, it depends how we agree on things, but let's say I give you a pair of numbers. That's a much more simple case than the distribution. One number is the accuracy, the other is the probability, and what you promise is that your oracle will satisfy this accuracy with this probability. Okay, so why do I have to give you different accuracy and probability? Why can't we agree ahead of time? Because you may be able to provide this at different cost. So there's a concept of a cost. Imagine that you have to sample more, right? To provide more reliable, more accurate oracle, you have to sample more. And I may or may not want you to do that depending how much accuracy I want in my algorithm. So I should have the flexibility of telling you, hey, you know, work a little bit harder now. Same thing with discretizing PDEs, same things with you know, a whole bunch of oracles that exist out there, almost all of them in fact. You can control the accuracy by working harder. And I think this is something we should be able to incorporate in a definition of the oracle. On the other hand, there are also limitations. You can say, I cannot possibly deliver accuracy better than 10 to minus 3, no matter what. And that is basically tells me like, okay, I have a set, and any pair in that set will be okay. And so we have to agree on what kind of pairs you give me. And these are examples of these sets. These sets are in two-dimensional spaces, and these are not made-up examples. These examples all have papers written about them. They're just not explicitly stated this way, not in most cases. So there are oracles, first-order oracles, zeroth-order oracles that all kind of come from, you know, these, basically, they can spit out a estimate that satisfy a probability and the accuracy anywhere from the set. And like this, for example, corresponds to exact oracle, and this corresponds to something that you can satisfy with a given, this is bounded noise, whatever, this is all written here. So they all have papers written about them. So this is an interesting way to think about, but we're still thinking about the best possible way to express these. So if you have ideas or if you have oracles that I didn't present here that you want to throw at me, that would be good. I just right now started to learn about matrix vector multiplications that are an analog, that are yet another type of inexact oracle. So you can compute matrix vector multiplications inexactly, and the stochasticity. There's a stochastic component and some other noise component, and it just comes out of hardware. So it's none of the things that I've listed, but I don't know yet enough about it to talk about that. Okay, and these are the papers that have this. So essentially, the idea of what we're trying to do is like, let's try to create this little world of oracles, describe them properly, and then say that, okay, well, here are the algorithms that work with this type of oracles, and then no longer, we can mix and match, basically, algorithms. So if this algorithm works for derivative-free, randomized gradient estimation, it will also work for something that it comes out of machine learning with, you know, this assumption that there's no absolute error and only relative error. This kind of things. Okay, well, thank you.
Thank you very much for the talk. Are there any questions? So if you have a question, please wait until I'm passing you the mic so we get it recorded.
Thanks. I really enjoyed that talk. Yeah, I was wondering, for your stochastic oracle, if you have it for some value of failure probability, can't you just boost the failure probability, I mean, the success probability, boost it to 1 just by doing it over and over and taking the median? Or is there some limit that prevents you from doing that?
No, yeah, it's a good point. You may not need, right. So you could, I mean, yeah, you could. But it comes at a cost, and maybe your algorithm doesn't need that, for example. So like a whole bunch of, things that we worked with, like including something with Courtney, right, the line search, we were just assuming that if the gradient fails, you'll do something, and you will not care that it fails. So that's a whole other thing, is like boost. So you can, we don't assume we know that you violated the bound, right? Because how can you measure? So then you always have to keep on running it again and again. And ultimately, you will always have some probability of failure, just small enough. Right, yeah, exactly, yeah. And then the whole thing is like, if the algorithm, say, works, if probability of failure is less than half, then why would you even bother, right? Or in many cases, probability, what we analyze comes out that probability of failure less than half works, but there's a constant that is like 1 over 1 minus 2 times the probability. So that constant will explode as p goes to 1/2, so you choose p that you want to keep that constant what you want. Basically, you have a choice, yeah.
Thank you.
Is there any other questions?
So knowing a little bit about variational quantum algorithms, they seem like they're exactly the stochastic oracle that you're thinking of. Have you talked to anyone who works in the field?
So maybe, in the sense that I personally did not actually get into that myself, but my former student, Matt Menikeli, who's at Argonne, and my current student who was spending a summer there, they were extending some framework. So they were not looking at the oracles or describing them. They were just applying an algorithms that work for these sort of oracles to that. But that's a good point. I should probably extract from them the essence. I don't know if they even, so very often people actually, so this is why we're trying to write this survey, is because we want to say, okay, here are the things we can characterize. Can you tell me what kind of oracle do you have? Yeah. But it's a good point. I should probably reach out to them.
Yes, we still have time for one short question, if there is any.
Just one quick question. In that probability bound, you have the norm inside the probability bound. Okay.
Yeah.
I'm just wondering about the norm. Is it applies to all norms or specifically for?
I mean, I am thinking in, so this is just the definition, right? You can write definition any way you want. But in most cases, in most cases, we want two norm just because we know how to deal with, just more immediate how we plug it into the theory of an algorithm if we have a bound on a two norm. I mean, if you have something, if you just happen to have an oracle that produces a bound on a one norm, then either you have an algorithm that can work with that directly, or you just, transport it into two norm. And then, then you have dependence on dimension. It's not as nice, but.
Just before we finish, there is a reception just across, has a corridor in 5511. And thanks again for the talk. And please join us for the reception.
Thank you.